All right, hello. Um, for my project today, I'm going to be talking about Aloha and its origins is where I'm going to start. So, Aloha was actually the first ever Mac created in Hawaii in the 1970s, which is where the name comes from. And Mac stands for Medium Access Control. So, basically, this sublayer is just something that controls interactions between optical, wireless, and wire transmissions on a hardware level. And the concept was created by Norman Abramson. Basically, he just wanted to create a connection between people on remote islands, and so he tried to use computer systems to do this because they had no telephone lines at the time. And so there was a problem of multiple users all competing for the use of a channel, and so he discovered the solution is send frames using radios and frequencies to a central computer in order to let people communicate. And so eventually this was expanded, and there's now two versions, which are pure and slotted. So Pure Aloha is the first version. This is the original. And so, given the fact that Aloha consists of constant data transmission from multiple computer stations, there's bound to be collisions, as you see here, like in football, which can cause frames to become corrupt or damaged. And so, the reason it's actually called the pure version is because there's no checks that occur to prevent these collisions. And so, the collision usually occurs when a piece of data is sent to a channel that isn't free, and this is part of a contention system. And so this is a contention system is when multiple users are all sharing the same channel. And so as seen in the diagram below listed, the gray areas actually mark the collisions because there's two frames occupying the same channel and they're overlapping and destroying each other. And so in turn, a retransmission will need to happen at a later time after this collision for the data to be sent successfully. And so now we're going to talk about efficiency. So to check the efficiency, you can actually use the Poisson distribution. And so this just calculates the probability of events that occur within a specific interval of time, or maybe events that have a constant mean rate, which is what these are. And so here I just did a quick example. If we use the letter F to show frames being certain amount of time, and F is greater than one, then we could assume that there's a collision because there's more frames being generated than the channel can handle. And so if we want to calculate load, we can represent that using L. We would use the mean per frame time, which is the mean rate, which I said was M, and times probability, which we know is P0 in math. And so it just looks something like load equals M times the probability, and that would be the load. And you can also calculate the probability that a frame will arrive undamaged using the same concepts and using the same distribution. But no matter what equation you use, there will never be a 100% success rate because there's always going to be collisions. And so now we have slotted Aloha. This is actually the second version of Aloha. And so this is a next iteration that was created to improve on the shortcomings of pure Aloha. And so the whole idea was to divide them into intervals so that frames could have their own slots. And so these slots had fixed time intervals that required users to actually wait before the beginning of a new slot before the data was sent. And so previously in Pure Aloha, obviously we saw a station was allowed to send data randomly at any point, which is why there was constantly collisions. And so as you can see below, the diagram that I just showed looks a lot different than Pure Aloha. You don't see any overlaps on the same channel. You see every frame is in its proper slot. And so we can calculate the vulnerability being cut in half because of this. And so if we use the same variables from before. If we wanted to calculate the load of slotted Aloha, it would be ME raised to the negative M. And that's just the probability that there will be no other traffic in the same slot as a specific frame. So as you see in the diagram below, all the frames are in their proper slots. And so now the last thing I'm just going to talk about is a little bit of fun facts. Slaughter Aloha was actually forgotten about for a long time and went without being used for years. And it was actually only reused with the creation of cable internet because multiple users needed a way to share the same channel again. So it just shows how like some protocols might be created and not used, but at a later time they might have a good use case that people need. And the final thing would just be that Slaughtered Aloha was actually not created by Norman, but it was actually created by another researcher in 1972 who went by the name of Robert. And that's my presentation. Thank you.